Hi students, welcome to Math Question Bank 23. Today I am going to discuss 5 questions and these are about simple differential equations which are often asked in different interview setting, different tests and so on. These equations typically require you to know only calculus. So if you are somebody in high school, you should also be able to understand this particular video. And certainly if you are somebody who wants to ask questions, these questions are some of the simplest questions in differential equations which you can ask. But still you will be surprised that many candidates are going to be stumped by these particular questions. I am Dr. Ganguly. So let's begin with a very simple differential equation, that is dy by dt is 25 minus y and y0 is 10. So these kind of problems are sometimes also known as initial value problems or IVPs. So in today's lecture, all the 5 equations are of the sorts that some condition is provided and the equation is with respect to time. So what of course we have to do here is we have to find the solution y as a function of t. So let's try to do that. Now when you look at this equation, you can clearly see that you can separate it into two parts, that is you can rewrite the equation such that on the left hand side you only have y and variables related to y present, and on the right hand side you have variables related to t being present. And once you do that, you write it as dy by 25 minus y equals dt. Then we can essentially integrate both sides here. So now if you want to integrate these sides, one of the things you can of course do from calculus is you can make a substitution, that is z or z is 25 minus y, and you can then say dz is minus dy. You can replace it in the left hand side and this simply becomes dz divided by z, because dy is minus dz here, and this equals integral of dt. So this is a simpler form. We can immediately write the integral as minus log absolute value of z equals t plus constant c. Now here many students make a mistake of writing this as log z. Actually it should always be log absolute value of z, because of course you know that log is defined only for positive values of z. So this is an important step which you need to make sure the student is actually following. Now the next thing we do is we make the substitution, that is z is 25 minus y. So we write this equation here where I have simply taken the negative sign to the right hand side, or I have multiplied this equation on both sides by -1. So I then get this equation here. Now I can immediately raise both sides of this equation to the power of e. So I will get the absolute value of 25 minus y equals e to the power minus t minus c, and then I can write that 25 minus y equals plus minus e to the power minus t minus c. So this plus minus comes here because here you have the absolute value. So this particular value here, this is going to be free in sign. So this is the equation. Now remember this, I'm going to take it to the next slide. So I take this equation to the next slide, and then what I do is I can write out the expression for y. So I can write out y is 25 minus plus e to the power minus t minus c. Now here I can write this as 25 plus a e minus t if I define a as minus plus e to the power minus c. So this is a very interesting step which you can do here. And then what I'm going to do, I'm going to calculate the value of a by using the initial condition. So what I do is I know that y0 is 10. So I put y0, and y0 is going to be 25 plus a, because e to the power minus 0 is 1. So I get 25 plus a is 10, and then I can immediately solve for a. So a is going to be -15. So I get the solution as y is 25 minus 15 et by putting the value of a in this general equation for y. So now we have obtained y as a function of t. Now let's just check this. So to check this, what you need to do, take the value of y and we are going to differentiate it. So remember, the equation in red is the equation we started with. This equation in green is the solution. So let us differentiate dy by dt. So I'm going to immediately get minus 15 into minus 1 e to the power minus t, and then I'm going to get 15 e to the power minus t, and then if we look at the solution, I can write this as 25 minus y. So immediately I can see that this satisfies the differential equation. We should also check for the initial condition. So of course we see that if y is put to 0 in this green equation, then I get 25 minus 15 e to the power minus 0, and this becomes 25 minus 15 or 10. So essentially this equation is something which satisfies the initial condition. So let's plot this equation. It's always a good idea to ask a student to plot an equation or to plot the solution, because that sometimes gives you an idea about the response of the system. So this is the response of this particular dynamic system, and you can see that y as a function of t is something like this. So essentially it does satisfy the initial condition here. So y0 is 10, and then it grows like this. So let's now look at one more differential equation. This is a very simple equation, but you will be surprised that this simple equation can model many growth phenomena out there, for example, in population and so on. So this equation is dy by dt minus y equal to 0, where y0 is y subscript 0. Now this equation can be very simply solved, as we can write it in this form immediately here. So we can separate the terms such that all the terms involving y are on the left hand side and all the terms involving t are on the right hand side. Then I can essentially do this particular calculation. I can integrate both sides and I immediately get log y is t plus c. Now once again remember, log y should be put in terms of the absolute value of y. Now I can write the absolute value of y is e to the power t plus c, and immediately I can get a solution as y is plus minus e to the power t plus c. Now this absolute value step, like I mentioned before, is important because log is defined only for positive values of y. So I write this solution as a e to the power minus t. Now here a is defined as plus minus e to the power c. So what we can now do is we can figure out a by putting in the initial condition. So remember y0 is a e0. So that's coming from this solution here. And of course e to the power 0 is simply 1. So I get a is y subscript 0. I put it in the equation here, that is y is a e to the power t. That's the general solution, and I get the solution as y is y0 et. Very simple solution, and you can see why exponential functions are so important, because this simple growth model which is there in differential equations, the solution comes out as an exponential, and of course there is the initial condition which controls this particular phenomena. So let's just check it. It's a very simple exercise. We simply differentiate this function. You immediately get y0 et, which is simply y. So the differential equation is satisfied. And also you see that at y0, you get y0 e to the power 0. E to the power 0 is 1. So this gives us y0. So if we plot this, we get this particular curve, which is in fact the solution to many growth problems out there: population growth, bacteria growth, growth of many kind of things, and so on. And all these growths can be modeled as y is y0 e to the power t. Now to plot this particular graph, I have used the value y0 is 1. So you see this is starting from 1, and then this is growing exponentially. So this is the exponential growth model. So exponential functions are very important because they come out as solutions of some very important but very simple differential equations which model a lot of physical, biological phenomena, and so on. Now if I simply change the sign from minus to plus, I get this differential equation, and this actually is the decay differential equation: dy by dt plus y equal to 0. Y0 is y subscript 0. So let's try to solve this equation. So of course you know the solution is going to be pretty similar to what I did last time, and in fact you do the same processes here. You actually split the problem into two parts. So you have variables of y here, you have variables of t here. You integrate both sides of this equation, you get log absolute value y is minus t plus c, and so you get absolute value of y is e to the power minus t plus c, and you can write the solution as y is plus minus e to the power minus t plus c is a e minus t, where a is defined as plus minus e to the power c. Now I can immediately calculate the value of a by invoking the initial condition, that is y0 is ae0. And so from here you can very quickly see that a is y0 because e to the power 0 is 1, and so I get the solution as y is y0 e to the power minus t. So this minus t is the term which actually causes this particular response to decay. So that's the big difference the minus sign makes. Let's take a look at the solution here. We can check it out by putting it in the differential equation. So dy by dt is given as follows here. So there is a negative sign, and so you end up with negative y. So dy by dt plus y is 0. Also we see that y0 is satisfying y subscript 0. So the differential equation is satisfied by the solution, as well as the initial condition is also satisfied. Now let's plot this, and now you get this decay model. The decay model is often useful in, for example, radioactive material decay and so on. So many of those phenomena are actually modeled by this type of decay equation. So again, remember here I have used y0 is 1. So this graph starts from 1, and this is the typical graph of exponential decay. So you see exponential functions can model the growth of things. It can also model the decay of things. Now let's try to create a problem which is more realistic, that is the logistic growth equation. Now this is also pretty widespread in problems, and here what happens is that you have growth, but then after some time the growth may taper off. So this is a more realistic model in many problems such as those involving population growth. So let us look at this equation. Dy by dt is y into 1 minus y, y0 is y subscript 0. So now what happens is, again we take this equation and immediately we can split it such that left hand side are the variables of y, right hand side are the variable of t, and we have to perform an integration on both sides here. Now before we even perform the integration, we know that we have to write this in some form of partial fractions to do the particular integration uh, here. So we do that, we take this particular function 1 by y into 1 minus y and write it as a by y plus b by 1 minus y, and I can expand it out like this. Now from here I can immediately write some equations by taking this part, the numerator term, and equating it to 1. So I would get a minus ay plus by equals 1, and from this equation I can write that a would be 1 and b minus a would be 0 by taking the coefficients of constant term and y here. And so from this I get a equals 1 and I get b is 1 because b is equal to a. So I can then write this as the integral dy by y1 minus y is integral dy by y plus integral dy by 1 minus y. So the splitting in partial fractions is a very standard approach when you are dealing with these kind of problems. And so right hand side is of course going to become t plus c, that is the integral of dt. Now immediately I can write this as log absolute value y minus log absolute value 1 minus y is t plus c. So remember this 1 minus y type of function here is going to throw a negative sign here because the negative y is present here. So this is the equation, and now we are going to try to simplify it further. So we start with this equation here, and I can immediately write it in this form. Remember, log a minus log b is log a by b, and then I can further simplify it by taking exponentials on both sides. I can throw the plus minus here by removing the absolute value, and I can write this term as ae to the power t as we have done before. So essentially a is plus minus e to the power c here from this particular equation. Now here I have this thing, and I can immediately use the fact that y0 is y subscript 0. So we do that here, we put y0 is y subscript 0, and so we get this particular solution here. Now at this point you can clearly see that what has happened is that I have taken this equation here, I have substituted here y0, so I have got y subscript 0 here, and on this side I have got a e to the power 0, so this is a. So a is y0 by 1 minus y0. So if I substitute that in this equation, I get y by 1 minus y equals a, which is y0 by 1 minus y0 into e to the power t. So these two equations in pink are simply the math about how A is calculated. So now we are going to take this equation and we are going to figure out y from this equation. So what we do is we take this equation and we actually take the reverse of this equation, that is we flip the numerator and the denominator, or we take 1 by this term and 1 by this term on both sides. So once I do that, I get this equation here, and then I simplify it further in this form. So here I'm taking, for example, 1 by y minus 1, here I'm getting 1 by y0 minus 1 and e to the power minus t. Now from this I write a simpler form like this here, and I get the solution of y, which is given in green. Now you can see here the solution of y as a function of t is expressed in terms of y0, which is a known number here, and e to the power minus t. So this equation in green is the solution of the logistics equation. So now let's just check this. Let us first put y of 0, and if we put y of 0, we get this simplified term here. So e to the power minus 0 comes, that terms becomes 1. So I get this equation here. So here I would get 1 minus y0 by y0. And so after some simplification, I get y at 0 is y subscript 0, which is the initial condition. Now to check the fact that this equation satisfies the differential equation, let us write y in a more simpler form, that is 1 by 1 plus b to the power e minus t, and then I can see dy by dt is this particular term here, and this is equal to y e minus t b by 1 plus b e to the power minus t. Because remember what I did here is that I took the value of y here and I realized that I can substitute one of these terms, that is 1 by 1 plus b e to the power minus t, with a y here. So I get a slightly simpler form. Now continuing on that, I take the value of y, I take the value of dy by dt. Now I can write 1 minus y as 1 minus this term here, that is y. I can simplify it and I get this term here. Now comparing this term with this term here in dy by dt, I immediately realize that dy by dt is y into 1 minus y. Remember, y was this term here and 1 minus y is this term here. So this of course is the differential equation. So I have checked that this differential equation is something which is satisfied by the solution we have created. Now let us just try to plot it. So I have tried to plot it for the case y0 is 2, and in that case the solution comes out something like this. Now of course this solution is going to vary a lot depending on the value of y0, and also many of the constants here I have put to 1. Those constants will typically be different for actual problems. Finally, let's look at one simple trick question. This is slightly tricky. It's again a very simple question you can do by calculus. So this is solve the differential equation dy by dt plus 2ty is t, y0 is 0. Now, this problem becomes very easy to solve if you realize a certain thing, that the right hand side has a t and you could write it as 2t by 2. So if you realize this, then you can simply write the right hand side as 2t by 2 and subtract 2ty, and then you can take the 2t and write half minus y. So this equation becomes separable into one part which is related to y and the second part which is related to t. Now, most frequently you can give these types of problem in many questions because the actual theory of differential equations gets very complex, gets very cumbersome. So you don't expect people to remember those things when you are asking them questions directly on the blackboard or the whiteboard or on Zoom or Team. So it's easier to ask questions which can be split into separable part, but many problems can be devised where something can be taken to the right hand side, split up, and you end up with a separable differential equation. Now, of course, I again do the usual integration. I get the log term on the left hand side. Here I get 2t square by 2 plus c, t square is plus c. And again remember, log has this absolute value here, and the negative sign comes in because I have the minus y here. Now I write it like this. So essentially I've multiplied this equation by minus 1 on both sides, and then I take to the power e on both sides, and I get half minus y equals plus minus e to the power minus t square minus c. Now, as before, I take this equation and I have this equation for y, and I write it as half plus a to the power e minus t square. This is the general solution. And then what I do is I invoke the fact that y0 is 0. So again, if I invoke that fact, I get y0 is going to be half plus a, because if I put t is 0 here, this is going to be half plus a. So this is 0, so a becomes negative half, and then yt becomes half minus half e to the power minus t square. Remember, this a I got as minus half, so I got this equation here, and final solution becomes 1 minus e to the power minus t square by 2. Now what I do, I want to check this. So I take this equation here, the solution. I put y0. I immediately get 0 here, because if t is 0, then this becomes 1 minus 1. Remember, e to the power 0 is 1. So I get y0 is 0. Also, I can differentiate this particular function. I get this here. And then I can immediately see that e to the power minus t square is 1 minus 2y. That's from the equation of the solution itself. And then I can easily write dy by dt is t into 1 minus 2y. That is, I substituted e to the power minus 2 square here, and so this gives me t minus 2ty, and that immediately gives me back the actual differential equation. So this particular solution does satisfy this differential equation. Now before we end this problem, let us just plot this function here. So again, this plot is nice. It kind of starts out like this, again comes down like this. So it's an exponential function, but it is related to minus t square. So that's giving the more nonlinear factor in this particular equation. So today we looked at 5 very simple differential equations, which are very good questions. I have often seen such equations being asked in different questions. These may be if you are going for some kind of university setting, or it may even be for some STEM jobs. So again, even if you are reviewing math, it's a good idea to look at such questions. Now in the next question bank, I'm going to look at the predator-prey equation, which is a set of two nonlinear equations which are extremely important and which are very frequently asked in different questions and different test problems. That is certainly going to help you increase your math knowledge. Now, if you have any particular ideas about what to add in the question bank for further lectures, please let me know in the comment section below, and I will keep including them, because I plan to make this on and off, and hopefully this will be a good question bank which will be useful for review as well as for people who want to ask questions. So you can then kill two birds with one stone.